Yeah, this presentation is somewhat complementary to the first one. This is the introduction to column store indexes, where the first presentation today we focused on B-tree indexes and its sweet spot for OLTP and mixed workloads. So this presentation does have a lot of slides that do refer to B-tree indexes that I'll kind of just skip over since we already covered them today. But I'll still try to focus on just the differences between the B-tree approach and the column store approach for some of the indexes. So I'll talk a little bit about the traditional disk-based row store B-tree indexes. But I won't talk about them in depth at all because of our last presentation. I'm mainly going to focus on the architecture of column store indexes and compare and contrast those with the row store, B-tree indexes. And really the context is about, what, it brings to the table nowadays in SQL Server is the ability to do, near real-time analytics, leveraging the column store index structures compared to, the limitations that we used to have. Column store was really introduced, I think, back in 2012, if I remember correctly, but it was fairly primitive at the time. The product or the feature has really grown since. It started out as only read-only non-clustered column store indexes, so that made things very limited. Fast forward, a decade, and now that we have the ability to create, everything updatable and, keep the data, updated in real time and fairly efficiently, you can actually put column store indexes on OLTP workloads for certain use cases if you need to have near real-time analytics that can benefit from column store. So, just keep that in your mind when, throughout this presentation. That's really what I'm getting at. Compared to the traditional data warehouse approach where it's kind of a no-brainer to use. Oh, shoot, I wasn't sharing. My bad. Sorry, didn't start it. Oh, I have to restart the sharing here. Get out and back in. Maybe that'll work. For some reason, it just wasn't advancing to the next slide. So let me try this again. All right. Already talked through that slide. Excuse me. So really, all relational databases are logically organized as a table with rows and columns. The underlying storage is almost an implementation detail from a query perspective. You query a database with relational or should I say traditional B-tree indexes the same exact way you would with a column store index, clustered or not. It's really all behind the scenes. The physical table organization, though, even though it's transparent, it does give you some, control and benefits to organize, or use column store indexes compared to the traditional B-tree row store indexes. So we have the choice, as I mentioned in the last presentation, that on a regular row store, or you can organize a table as either a heap, a B-tree, but you can also use, a column store organization, meaning that you have a clustered column store index as the table. So then you don't have any row store at all unless you create non-clustered row store indexes. And exactly how you mix and match the traditional B-tree indexes with the column store indexes kind of just depends on your queries and workload. But what column store brings to the table is really, optimized more for scans, whereas the traditional row store tables or indexes are, optimized for a compromise between the, equality singleton, look up a single row versus, scanning a lot of rows. Columnstore is more structured around being able to do, large scans. So with a regular row store, you have pages and the rows are actually stored in the pages. So each row, contains, can have multiple rows inside, or each page, I should say, can have multiple rows inside of it. Whereas, your only choice really is just whether or not it's a B tree or, a heap. Your only options there to reduce memory or really page, in row compression like we demoed last session. So with the row store, you basically have multiple rows per page. I kind of discussed this in the last, presentation a bit. Unique, non-unique, included columns, filtered options, and all that kind of stuff. Don't need to talk about all that stuff. So the summary from last presentation is simply that, the idea with OLTP indexing and B-tree indexing, you want to try to create the indexes to facilitate touching the least amount of data possible, just the data that you actually need. And there's a bit of a strategy behind it, and hence the whole presentation we just went through. However, there are conflicting goals, of course, between, having maintenance and too many indexes. Columnstore, though, takes a different approach. But instead of storing the rows row-wise, meaning that you have multiple columns in a single row, they actually have each column in a separate structure called, or should I say, each row, or each column is in a separate structure called a column segment, and they store those segments in groups of rows that can have between 100,000 and a million rows each. So really what it's doing there, and I'll have a little diagram on the next couple slides here that'll help explain this better than I can in text. But the idea is that columns are stored, in their own individual structures. So you don't have any page that has multiple columns or multiple columns from different rows in it. It's always going to be the same column of the table. And each of those column segments, which is essentially the group of, up to 1 million rows, it's compressed and stored into lob pages inside the database. So it's really nothing more than a large object, not structured rows like we have in a row store. So that helps compact space quite a bit because the data is compressed as it's put into those lob pages. And then the larger row groups, etc. The larger the more number of rows you have in a row group, the better your compression is going to be, because it can actually keep a dictionary to reduce redundant values and compress the data quite a bit more than you normally would. That's beyond just the it's a different sort of compression technology than we have with the traditional page and row compression we have on row stores. Order matters when it comes to inserting into the column store, and that if you can insert the data in a particular order, it can improve the compression quality. And with new SQL Server 2022 is a new order option on the create index statement that allows the rows to be essentially sorted as they're being loaded into the column store, which improves the the amount of compression it can do, as well as segment elimination that I'll discuss in the upcoming slides. Importantly, though, Columnstore is memory hungry. You need to have a lot of memory to be able to have larger row groups, and larger row groups, help improve the compression and all. So, the more memory, the better when it comes to Columnstore, especially when it comes to, when you're creating index and loading Columnstore indexes. So this slide probably shows the Columnstore index a bit better than I could speak to, but each of those columns in this first part, in this top half here, each of those, bars represents a separate, segment. And those segments are really just the compressed column values, of up to, about 1 million rows or so. and each of those bars is a separate column. And the reason I think this diagram really just shows those bars at different heights isn't because they have a different number of rows. They all have exactly the same number of rows in them, meaning, row, which corresponds to the number of rows in the, row group, but rather they vary, the compression on a given column will vary depending on how many identical values and other factors that there are in, that row group. So if I load this table, in let's say sequence by customer ID, for example, if I order that, because the data is already ordered by customer ID, the first 1 million rows, if I have large customers, will tend to have the same customer in it, whereas the other row groups, as they get loaded, they're going to have different customers. If I have the input data set sorted that way. So that way, it only has to, in store just the, the data that's not redundant inside of the column store segment. So that's why it compresses very well. But order does matter as you load it, if you have control over that order. If it's strictly like insert order, by trickle inserts where you insert one row at a time, essentially, or a few rows at a time, then you're probably not going to see as much of a compression unless that data coming in just happens to be ordered in a certain sequence. So each one of those, so that top half of that diagram represents one, column store segment. The bottom half is another column store segment of, let's say, another million rows. So in this example here on this page, you would probably, this would represent 2 million rows in a table. And you can have as many, column store segments as you need to fit the data. And each of those segments may compress differently depending on how many, duplicate values or how well the data compresses in general. As a separate structure, then the column store, they have something called a delta store. And the delta store is really a group of B-tree indexes, traditional B-tree indexes, mind you, that's kind of internal to column store indexes to be able to handle any changes to the column store index. As I mentioned initially, before they invented the delta store, back in the 2012 days when column store indexes were read-only, you pretty much had to create the column store, non-cluster column store index on a row store table. And then if you wanted to change some data, you had to drop the index, update the table accordingly, or and then recreate the index from scratch. The delta store is almost like a little shadow B-tree index to be able to hold any of the data changes. When data is deleted from a compressed column store segment, it's really just a shadow delete. When data is inserted or updated, it's really just a shadow update or delete where the changes are actually in the delta store, not applied to the column store initially. Then what happens is that when you query the data, SQL Server internally uses both the compressed column store and the delta store to return the current values of all the rows and columns in the table. And that's all internal behind the scenes. But all that said, it is a consideration, and that's why I'll be talking about that a little bit more as I go through the presentation here. But the delta store, there's one delta, what they call it, a delta group, basically, a delta row group for each column store segment. So you're going to have one of the, even though this diagram here only shows one, well, it says one delta store. The delta store is really the collective name for all the delta row groups in the column store organized or in the column store table. So in this diagram here, that yellow highlighted, hopefully you can see that well. Okay. Anyway, the column, one of the columns is highlighted here, meaning that if I were to in the in the columns, let's say this is so in this column store, if I only select one column, select column A from table, and it's I have a cluster, and that's a clustered column store table, it would only need to touch that one column. It wouldn't have to touch any of the other columns in the table, unlike a row store where it actually has to pull all the column values from the data page for each row, that are in there. It only has to touch the values for one column. and it entirely ignores the other ones. It doesn't have to, touch them at all. But of course, I can have as many columns as I want in my select queries. So, you can have multiple columns, but then it has to touch each one of those that you specified. But column store indexes are a good reason never to specify select star from your table, because you'll be just, have terrible performance compared worse performance actually than compared to a row store table, where with the row store table, at least you already have all the columns, in your hand when you read the, the data page. But in the case of a column store, you're wasting a lot of resource if you're asking for, columns that you don't need. So once compressed,
yeah.
read only, that Delta store that I spoke to exists, essentially as a shadow copy of the current data, for the changes to the row group. There's a separate process in the newer versions of SQL Server called a tuple mover that will actually take the B tree, data from the Delta store and apply it, to essentially essentially for all practical purposes, rebuild the column store index in the background, to make them compressed again. That way, the data, doesn't waste as much space, because while it's in the Delta store, it's going to be taking up the normal amount of space as it would, if it wasn't compressed at all.
I think Morelli has a question. Morelli, do you have a question?
Yes, I do. Thank you. So for the column store, are you able to hear me?
I can hear you. He can't. So go slow.
Okay. So let me try and say this. So column store is gonna help us select only specific columns, and the compression is better for that.
Column store is only going to allow us to select specific columns, and the compression is going to help on that. Okay, go on.
So why, and most of our queries use only specific columns. So why are we not using column store as a default index instead of using row store?
Most of the queries only use specific columns. So why aren't they using column store indexes as a default versus the other indexes, the B trees?
Sorry, Julie, I think you, Dan is muted. You want to unmute.
One second. Hold on a minute. Dan, it looks like you're muted.
Oh, I'm sorry. I was fiddling trying to get the speaker working. I must have accidentally muted myself. Sorry.
Okay.
All right. So if I understood the question correctly, it's essentially, since most queries only select a subset of columns in a given table, why isn't column store the default storage instead of row store? My answer to that is column store is mostly optimized for large scans, whereas row store is optimized for both point lookups, where to retrieve single rows, as as well as range searches, like I discussed in the last presentation. It's not quite as optimized for full scans, but it still does a halfway decent job of full scans as well. So it's not column store. On the other hand, the only way to retrieve a row is to read all of the I shouldn't quite say that, but anyway, it's optimized for scans of the large scans of the table, rather than the point lookups like the regular B tree index structures are.
Okay, thanks. So
I think.
Yeah. Yes. Will that kind of so column store and row store for column store for the columns that we are using in that query, and row store for specifically identifying the predicates, will that help identify the matrix that we're going for and speed up the query a lot more? I know that was a quick
Oh,
question.
you're driving and you can't type this in. Oh, so you're talking about Columnstore, but then you're talking about row store?
Yes, so using
What?
both of them, so Columnstore helps us only get a select set of columns, but the row store helps us identify the predicate within those columns. Will that help us to narrow down on the metrics that we're trying to display or have in a
So
query?
Columnstore is narrowing, is what they're going after, is how they're going after the data, but row store is applying to the predicate. So wouldn't putting both those in play assist with reducing the data and assisting with the performance? Did I get that right?
I think so. Yep. Thank you. Thank you.
So that's the question about using Columnstore and row store.
Okay, so the question is about using a combination of column store and row store on the same table. All right, yeah, so
Right.
So if you organize the table as a column store, all the columns obviously are going to, meaning that it's a clustered column store index, then obviously all of the columns are going to be, in that column store. And the column store by itself is optimized for large scans of the, of the table essentially, or the columns that you specified on your select query. Now, if you need to also do, for example, point lookups by a primary key or, some other smaller set where a row store index would be more beneficial to access the data, then you would need to create a non-clustered row store index on the table, which is perfectly okay on top of the clustered column store. So that kind of gives you a little bit of the blend of both worlds in the sense that you can do very efficient large scans on the column store, yet still be able to have specific queries or that that need access to point lookups in the data, but access to the columns in the column store organized table is a little more expensive than accessing, for point lookups, mind you, than it would be just a traditional row store type table, comparatively speaking, because it still has to go through the work to not necessarily decompress, but go through the work of finding the original value from the, as I'll show later about, from the dictionary and stuff, where it, avoid storing the redundant value. So you can have a hybrid approach, and that's one way to address the needs of both type workloads, the OLTP and the column store. But for that kind of a use case, typically what one would do is just create a regular row store table without necessarily having all the benefits of that compression, yet still create a non-clustered column store index on that row store table to have the benefits of the large scans. And in that non-clustered column store index, you would just have the commonly small set of columns that you would typically scan, rather than all the ones in the table. If that answers your question. If not, I apologize.
Yes.
Okay, thank you.
Thank you.
So some of the differentiators compared to the row store traditional B-tree indexes is that there are no key columns. They're really just a list of columns. So if you create a clustered column store index, you don't even specify any columns because it knows that all the columns in the table are the clustered index, or the column store clustered index, to be more precise. If you create a non-clustered index, you specify a column list, but that's really just a list of the columns that are part of the the non-clustered column store index. They're not actually keys in the traditional sense like they are on row store indexes. It doesn't matter what order you specify those columns in the non-clustered column store index because they're not keys. And similarly, it doesn't really matter what order the columns exist in the table for that matter. They're not keys. They're really just a list of the columns that are stored column-wise. Your options are either clustered or non-clustered, simply meaning that specifies whether or not the table is going to be organized as a clustered column store, or if it's going to be a row store and you're going to create a non-clustered column store on top of a row store. It's okay to have row store indexes on a clustered column store table, as I mentioned in answering the question a minute ago. Excuse me. You can have, I don't think there's any practical limit to the number that you can have. It's like 999 or something, if I'm not mistaken. But you can only have one non-clustered column store index on a row store table. So that one column store index would essentially, since they're really just a list of columns, it really doesn't matter. You wouldn't need to have more than one, frankly. They would all be essentially functionally identical if you had more than one. To having a single index or a column store index suffices. Your options when you create a column store is there's no such thing. There are no keys, so you can't specify if they're unique or not. There's no included columns because the list of columns essentially are almost kind of like included columns, I guess. You can have filtered column store indexes, but that's only allowed, as a non-clustered index on a row store table. You can't create a filtered clustered column store index. This one is a little bit of an eye chart, but I want to call out how column store has evolved over time here. The column on the left is when SQL Server was first introduced. Column store was first introduced with SQL Server, where there are just a handful of features that were relatively small handful of features that column store had. Most importantly, as I mentioned earlier, is read only, and because column store made your column store index made your table read only, that was a problem. That fortunately was addressed in SQL Server 2016, where you can have update, you can have you can do writable column stores. And so really, I would say it was really only, column store is really only really useful until once SQL Server 2016 Service Pack 1 came out, where they addressed a lot of those issues. And that's why in this chart, you see most of the features were available as of SQL Server 2016. And then there are a few features that were incrementally added since then. So I'm going to assume everybody here is on a supported SQL version, meaning SQL Server 2016 or later. So I'll call out the features that are available since then. That tuple mover I mentioned about moving data from the Delta store into the actual compressed, that background process was introduced in SQL Server 2019. So it runs in the background now. And also 2022, this is a useful one, where you can actually specify an order clause when you create a clustered column store index, which is really used not for ordering the index, but to help facilitate the compression, because essentially it'll do a sort for you as the index is created. And that can help improve compression, as well as segment elimination. So when you create a column store index in SQL Server 2022, you can specify a list of columns. And ideally, that list of columns in your order specification should match your common query predicates on your where clause. That way, the data will compress, fairly, or a little bit better, ordered that direction, because your identical values will be more or less contiguous. Plus, it'll be able to do some more segment elimination that I'll speak to in upcoming demo here, where it knows from metadata whether or not a given column store segment contains the rows that you're looking for, so it can eliminate those segments entirely during scan operations. Like with the B-tree index, the goal is you only want to touch the actual rows that you need for a given query. Well, once you get into Columnstore, your most granular level is mostly around touching the segments you need for a given query. And those segments are relatively large with 1 million rows each. So if you can eliminate 1 million rows from being scanned, that's only a good thing, even though the scan is very, very efficient with Columnstore. Still, not touching them is going to be even faster. Let's see. I did mention the segment. Okay, so I forgot to speak to that first bullet here. Each Columnstore segment has metadata associated with it that essentially has the minimum and maximum values of each column within that segment. So the implication is, if let's say a good example is if I load the table in date sequence, in chronological order, then the first 1 million rows will have a start and end date, and the next segment is going to have a different start and end date that's higher than that first segment. So if I do a query, and where date is the predicate, I'll be able to skip that first segment, and just touch the segment where that contains, only touch those segments that contain the date. So that can help, scan performance quite a bit. All right, so let me jump to demos, talk a little bit more about row groups and the segment metadata. Let's see. I'll make sure I start fresh this time. I forgot to refresh AdventureWorks this one. So I'm just going to create a little demo database. Let's see, so yeah, this will take a couple minutes. Let me speak to it while I'm creating it. Yeah, so here what I'm doing is I'm creating 3 tables. One is just a heap. I'm just using that as a source for my data. And I'm going to load that heap with 10 million rows. And in each of those rows, I have a column, which I have a primary key constraint on that table that's just an identity column, plus also 5 columns. I have an integer, a varchar, a date time 2, and a car column. And then I'm inserting a bunch of random, I shouldn't say random data, but generated data into that heap table. The first column, column 1, is going to have values from 0 to 1 million, basically. It's an integer. Second value is less selective. It only has values between 0 and 1,000 and 999. For the varchar column, I'm just generating essentially random type values between 0 and 9999. Then I have an incremental date column, and then finally another varchar column that's going to have values between 0 and roughly 100,000, but they're going to be generated in a random nature, which will affect the compression. Should have put a progress thing in here. I think this thing takes a couple minutes to run. But anyway, then I create a clustered index table and just essentially insert all the data, from the heap into the table with the clustered index. And then finally, I do the same with, the clustered Columnstore table. And really, so the test data is in the heap table, but I'm just inserting into both the the regular row store table and the clustered index, or in the clustered Columnstore index table. Let's see, let me close my previous demo stuff so I don't get too confused. Alrighty. All right, so that's a freshly created database that I just, I'm going to use that just to show you the data distribution here. So here I'm just doing a simple query. It doesn't matter which table I use because they all have the same, data in them. But the cluster, so in this case here, I just used the B tree table, the regular clustered index table. But you can see the maximum minimum values within the entire table here. Just to get the range. So here I just loaded essentially, so the date range here goes from the beginning to the end of 2018, roughly at by 1 row per second or something like that, along with those other value ranges that I mentioned. So if I look at the space use here, though, contrasting it with the clustered index versus the Columnstore clustered index, at first glance, it looks like their space is pretty similar, only slightly less on the Columnstore. But that doesn't really tell you the whole story because, as you may remember, I had a primary key constraint on the Columnstore, the clustered Columnstore index table. So because of that, it also has a row store, for that clustered index that requires a bit of space. So if I take a look at the space there, inside of the the database. I'll just do disk uses by partition because it tells you what the actual space is better. So the top one here is the clustered. I don't know how well you can read that, but the top one is the clustered Columnstore table, and we can see that the clustered Columnstore index only requires 180 megabytes of storage for the 10 million rows, whereas the row store primary key index, the traditional B tree index, even though it's just one column, it requires about 350 megabytes of storage. So about more than, or just about twice as much just to store one column value compared to all 6 columns actually in the clustered Columnstore table. The entry right underneath it, we don't care about the heap table here, so I'll just close that down, numbers table. But the clustered, the regular row store table requires 500 and some change megabytes. Basically almost the same size as just the B tree index, in the Columnstore table. So we did get the actual data savings for quite a bit. If I didn't need to have a primary key, I would just drop that, that I wouldn't have that primary key index, and my space requirements would be about, 20% or 30% of what the original table was. Yeah, we have a question.
Does using partitions change the 1 million row group and base it off of the partition?
All right, so the question is, we're talking about table partitioning here, I assume. So does table partitioning affect that limit of 1 million rows per Columnstore segment, or per row group, I should say? The answer is no, it does not directly. So you can kind of think about, in a way, conceptually, a Columnstore segment is kind of like a partition in the sense that it has, a specific number of rows in it. Well, actually, that's probably a poor statement, but anyway, if you put table partitioning, first it will consider which partition a given row belongs into, which will indirectly determine which Columnstore segment it belongs in. So try to think of a better example here. So let's say I have a yearly partition table, a table partition by year, and I insert a million rows. I'm sorry, let's say 2 million rows for the first year. I'm probably going to have 2, row groups in that first partition, each with 1 million rows. Now, if I turn around and I insert 2 rows for year 2, those are going to get into partition 2, and I'll end up with another segment in partition 2, for that, that new year. Then if I insert 10 rows in for year 3, those will get inserted into the third partition. But each of those row groups are going to be independent of the others in terms of the limit is concerned. So I'm going to end up with, two, row groups in the first partition, each with 1 million rows, another row group in the, second partition with whatever I said, 2 rows, and then just a few in the third year's partition. So what you'll end up with is more segments than you would than if you didn't partition the table. Because, first SQL Server has to determine what partition a row belongs in, and then it will insert it into the first, non-compressed row group, first one that's, still open within that partition. Yeah, feel free to follow up.
Does that make sense, Morelli?
Do we need no more clarification there, Julie? Okay.
Morelli, are you able to come off mute or? Thank you. Does that mean partitioning is similar to ordered column store index in the year example you gave?
I'm trying to think how to articulate my answer because I'm not sure I fully understand the question, but I think the answer is no, in the sense that the partitioning really doesn't affect the order of the rows within the column. Oh, actually, I take it back. Maybe I'm just trying to think out loud here, so please forgive me. Make sure I understand the question. So my analogy is probably not good. Let's say, for the sake of argument, that it depends how. So in terms of compression and inserting into the partition column store table, partitioning first will decide which partition it belongs into. So in other words, you'll end up with data in the right partition. But it doesn't actually affect the order of the rows, but it affects what partition they get put into. So the implication is, let's say I had a column called year with just the number of, let's say 2011. Then I have another partition with 2012, another partition with 2013, and then I load that partition table in random order. What would happen is that the rows with 2011 would end up in the first partition, which in turn, because they all have the same value, they would probably compress better than if the table was not partitioned and I loaded it in random order. And same thing with the second partition, because all the rows have the same year associated with it, they would compress better. So indirectly, it could affect the compression having that partition, on there. If you had large, row groups like that. Hopefully that answers your question a little bit better if I understood it correctly. there's a little different, there's a few different ways to kind of view it.
Yes, thank you.
The interaction between table partitioning and the ordering. So I just ran a query to just display the column metadata, from the, some of the, DMVs here, or catalog views. And so in this case here, after loading a million or 10 million rows, I have a bunch of compressed row groups, meaning that they're all completely full and compressed at this point. So it's all done in terms of those row groups. And I also have that primary key B tree index on top of this thing. So if I turn around and just insert an additional 10,000 rows or so, and just repeat the same exact query. Those newly inserted rows, it can't go into a compressed, segment. So it'll create a new, column store segment. And this one isn't compressed yet. It's in what they call open status, meaning this is the one that's going to receive, all of the rows, until, it gets to its threshold of a million, roughly a million, and then it will close and become compressed. So in the interim, the data isn't compressed yet, until it, fully gets, until it closes out once the table gets larger and once that one gets full. So I'll show some of the metadata associated with the table now, and we have, I think, 11 segments. Okay, so we have about 1 million rows in each one of these guys. And then, I guess I didn't. Okay, so I ordered this by the, essentially by the column name. So the ID column in segment 1, it's showing me the highest and lowest, what they call data ID, inside of these. And these data IDs essentially like dictionary, pointers to dictionary entries, or think about it that way. So this first column, which is the identity column, the ID column, it has, these are really mutually exclusive, ranges for the min and max within each column segment. So if I select a single row by ID, it's only going to, touch one or two of them, I think, whereas, for some of these other values, let's see if I can find them here. Yeah, some of these other ones have a wide range because I inserted essentially random values in this guy. I'm going to have to touch all segments for, these, some, if I select on just column 1. Column 2, it looks like it has a mix because of the way I, generated that test data. So, it's going to be kind of miss if you don't have complete, because, a lot of times you don't have complete order or control over when the table gets loaded. But, I wouldn't necessarily sweat bullets on it in terms of how much compression you get and whether that's 100% ideal. There's always some trade-offs you don't really have full control over anyway. So, just be aware of it, do the best you can in terms of trying to get, good compression and, segment elimination for your queries. It's never going to be perfect, but at least in my experience, but at least it's, not too bad. Let's see. Oh yeah, this is. Yeah, I just want to show the new order feature, SQL Server 2012 or 2022. So here I just take a snapshot of this before and after space, and all I did this time, I'm going to rebuild that clustered column store index. This time I'm going to order it by column 2. See how much better compression, savings I get here or not. We'll see. If I remember right, this does take a minute. So, Yeah, so what I'm doing here is actually it's going to actually have to sort the entire table, or try to, based on the available memory. I'm running on a laptop here, but it's fortunately it has enough memory to do this reasonably efficiently. By column 2, and then essentially load it that way. So what I would expect is that, after doing that, I'm going to see, better compression here. And I also should see, better, row group elimination, from because of the fact that all those values are in the same, or they're in different segments now. All right, so by doing it this way, it did reduce the size of the table, a bit. Let's see. And let's see. I don't remember if I ran this query before now. We'll give it a shot. See, that was column 2. Scroll right a little bit so we can see it. Okay, yeah, that was the one I did with the min max thing. So yeah, it's not going to apply there. Yeah, so it did compress better, but I don't remember why I have it. Oh yeah, that's just the ID, so they're still going to fall in a different range. So anyway, that's what I get for trying to do that ad hoc on that demo. So anyway, it didn't make the point I was hoping it would, but it did illustrate the reduced compression there. Let's see if I can see what the. Oh, I still have it here. I just refresh. Ready? Rebuilt the next 2. Segment metadata.
Does it matter which column you choose to sort on? Are there any specific attributes you look for choosing?
Yeah, so the question is, are there any guidelines for choosing which column to sort on? The answer is yes. Ideally, it will be the most common columns that you specify in your workloads predicates. That should, maximize the segment elimination. As part of the process. I think that's one of the reasons they, at least that was the guideline I recall meeting. I haven't 2022 production yet, so I'm kind of learning too. But that's what I recall is that, so you can have multiple columns or 2. I just threw one of them on there for that works. Let's see, I think I've most of this already. So Columnstore compression is very efficient, and Microsoft did a lot of attention to details as to make sure that the CPU overhead doesn't, offset the gains you get by reducing I/O and all. Plus the fact that it's compressed allows a lot more data to be fit in memory. That helps out too, reducing I/O. On my laptop, frankly, it's probably faster than most of the production SANs that you guys have to work with, just because I have local SSD storage, and you can't get any faster than that. Whereas a lot of us are probably constrained with HBA cards that are like 10 megabit and that kind of thing. So your throughput is going to be a couple of gigabytes maybe, instead of like here on this laptop, I think I can get maybe, I don't know, 3-4 gigabytes, per second, just for the SSD card. But, that's important when it comes to, Columnstore, because, if you're constrained on how fast you can get the data to SQL Server, these large scans, then having better compression is a big deal. It's just not going to be as evident on my machine. Demo. Oh yeah, I forgot to mention, there's also archive compression that you can specify that you can use to essentially reduce, storage even more. Unfortunately, I don't have a demo for that today. But of course, there's going to be more cost on CPU utilization, to decompress it as well. But it's a good, that in conjunction with table partitioning, I think is a good way to essentially, essentially keep the data online, but just instead of having physically move the file group or whatever to, slow storage or purge or archive data and go through a bunch of hoops, you can just simply, do archive compression on those segments to, the old stuff so that they're infrequently accessed, so you don't have to worry about the performance all the time, but it compresses very well. It uses like a gzip compression algorithm to do that. So you could actually decompress it in, in code if you wanted, I guess. See, I'm going to skip over batch mode. Essentially, a batch mode just allows you to, that will, it improves query performance, and newer versions of SQL Server, aka SQL Server 19 and 22, they both have a batch mode, both Columnstore and row store. Before SQL Server 2019, it was only available on Columnstore indexes. We're running a little bit long, so I'll try to hurry up here. Here I'm just simple select min max query from the row store table and the Columnstore table, just to show the execution plans real quick. Oops, forgot to turn on the show execution plan. Yeah, in both cases here we have simply a dump scan. It's doing a stream aggregate here. Parallel, plan. So really the execution plans have the same shape. The only difference is this is just doing a clustered index scan versus the Columnstore clustered index scan, or Columnstore, index scan, which is a Columnstore clustered index by coincidence. So it just aggregates all that stuff to return the results. If I look at the IO stats though, here I have a 69,000 logical reads for the row store table, and in the Columnstore table, see it read says 18 segments for this one. It was a parallel plan too. So anyway, so it scanned all of them, the segments in the table. But in terms of the so you take a quick look at the CPU time there. It looks like, I think it was about the same, right? Yeah, so it's just a little bit faster CPU time. So the Columnstore scan, was about 20% less CPU time. Elapsed time, it was pretty close to a dead heat. And then here I'm just focusing on a single column here, because that's the only thing I care about in my query. Same plan shape in work for the both of them again. For the row store, it didn't even bother to use parallel as clustered index Columnstore scan. Presumably because it didn't exceed my cost threshold for parallelism. It's a cheap query in SQL Server's mind. So if I look at the IO stats and CPU stats here, the first one, again, it's doing full scan, so that's always going to be the same. Let's see, the elapsed time now, let's see, 150 milliseconds. The way it's 0 milliseconds on the other one, on the, I'm sorry, 6 milliseconds on the Columnstore version of it. But the, you know, the number of, you know, see it did, yeah, so this is, it's because I'm doing the max, it looks like I'm not even going to skip any segments or anything here, but only had to do a single scan. So this essentially is comparing a query that's using a multi-threaded query against a single-threaded query. In the single-threaded query, the Columnstore even won the race, you know, even with one thread. So I have 12 projects on this laptop, so it's 12 versus 1, and the one won the race, you know. So Columnstore is that much more efficient, you know, large scans like that, especially when you're restricted to, you know, certain columns. This is not to make a note on why I put this one in here. Anyway, I'll skip over it. Yeah, so anyway, the theme is simply that, you know, the Columnstore, this because I'm also doing the group by, you know, so it's doing hash match, you know, I get that. Sure. It's still, you know, without beating the, you know, the row store on every turn, you know, for these large scans where I don't have any where clause or anything on it. See, I'm running short on time, so I'll just go ahead and show some of the segment elimination stuff. The, you know, here I'm just doing a data range query, and for a whole year, I'm only selecting roughly one month of data with each of these queries, you know, from that table. The, you know, because I don't have, you know, an index on row store indexes on date, you know, it's going to have to do a full cluster index scan again. It even has a nice missing index suggestion. For the Columnstore table, yeah, I mean, really, just look at the stats here. Yeah, so for the Columnstore table, it's still, you know, running a lot faster. But trying to remember. Okay, so here we have 7 segments, you know, on the clustered Columnstore table, you know, in this case here for the where clause. So, you know, that avoided touching the other, you know, instead of all 18 segments, it only had to touch that one. Let's see. I'll skip over that. Yeah, I'll just wrap it up here as good as time as any. So anyway, store, you know, at least in SQL Server 2016 Service Pack 1 or later, the 12 phase analytics on OLTP workload. I mean, Microsoft's enhancing the feature, you know, every version, as we saw on that, you know, on an eye chart that I had earlier. You know, so it's only going to get better over time. You know, works very well with Azure Synapse analytics as well as, you know, on-prem. And it's not just limited to, you know, it's just that, you know, it's just good stuff. I wouldn't say that replace your row stores with column stores, but, you know, it does have a sweet spot, and it's going to depend on, you know, quite a bit on the workload, especially when you have problematic type queries that do, you know, large scans. You know, even if it's not a, you know, a problem all the time, just having a non-cluster column store index, as long as your OLTP normal workload, isn't, negatively impacted, and you have sufficient memory to properly manage the column store. I mean, I would say definitely go down that path. Well, anyway, it's
So Dan, I know you're in a trading environment. Do you use a lot of column store indexes versus just the B-tree clustered indexes?
So the question is, in a trading, in a brokerage firm, basically, we use a lot of column store indexes as opposed to, B-tree indexes and all. The answer is for an OLTP workload, that I deal with, I use, pretty much, row store type traditional B-tree indexes for the most part. Do have, applications that could benefit, but I'm just a small person in this big pond, if you will. But I do have some applications that I deal with that would undoubtedly benefit considerably, that I'm trying to make the business case to do a rewrite on. As a matter of fact, we're slated for an upgrade to SQL Server, for that database, and I'm making the argument that we should go with SQL Server 2022, and along with that, introduce some changes to implement Columnstore, because it is a good case for analytic workload. Unfortunately, I can't speak to specifics about it, but it definitely is a good candidate. It's not something that I would use across the board. It's really for those workloads, like for example, in a lot of our trading type databases, we do not use any sort of analytics on the OLTP database. I mean, it is absolutely prohibitive just for risk management purposes, and for good reason. I mean, you don't have to, and don't. I mean, there's not, because usually the analytics are not going to be around. They're much of lesser of a business concern than the stability and the performance of the operational client-facing systems, if you know what I'm saying.
So are you saying then with the new version of SQL, you're recommending to take a look at the OLTP environment and maybe implement the column store?
Yeah. It's not like
on a case-by-case basis.
Yeah, that's the key. It depends on your workload. The one I was saying, the one application I was mentioning, I mean, it was screaming for Columnstore when they designed it, but unfortunately, the database developer who did it, we came from an Oracle background, and was not that familiar with SQL Server, and therefore didn't really explore Columnstore like he probably could have or should have, at the time. So it's something that, you just need to have as a tool in your toolbox, in my opinion. So if you're doing analytics today on a OLTP environment, then it's much more of a no-brainer, at least in my opinion. But if if you have an existing OLTP, application that you're not doing analytics on, then I don't think there'd be a good reason to introduce Columnstore, unless you have like tables that are, that are really large, and you want to save, storage, that kind of stuff, infrequently accessed tables, even if you don't, query them that often. And, it is absolutely a case-by-case basis. So, I'm not going to say, hey, jump out there, put Columnstore on all of your OLTP system. It's an option now. It wasn't an option just a couple of years ago. Now that with SQL Server 2019 and 22, it is. So I would definitely encourage you, considering it. If you got those big scans, there's no faster way to get the data. The documentation, by the way, on Columnstore is very good. I put I had a couple links on the deck. I also put it on the references on the last slide, but Microsoft did a really good job of, explaining it, and a lot better job than I did. It just had a lot with the, with these slides. It's hard to, without having demos too, it's hard to really discuss all the points. But I think at least in terms of documentation, they did a pretty good job of detailing, Columnstore, some load guidance for, data warehouse stuff where, that's been the traditional sweet spot for Columnstore, but also for, the OLTP stuff they're starting to move there.
Do you have your own like GitHub or site or location where you have where you post the queries and the?
I can put it out there. I haven't. I do and I don't. But I'll try to put one out there, public one. Yeah.
If you could put the queries as well as the slide deck, because I don't have a method of posting that right now. But what I could do is I could post a link, your link. I could send out a message saying, here's the YouTubes, and then here's the link to the slide deck and the examples.
All right. Yeah, I definitely want to share a lot of the queries and stuff, for both this presentation and the other one. I still have to do some cleaning up of some of the slides and notes and stuff. I left things pretty messy. I was in a kind of rush and didn't have a chance to, on the second presentation here and clean up a lot of the demo stuff. So I definitely want to do that before I post it.
Well, thank you very much. I think it was a great companion presentation, but thanks for discussing indexes with us this afternoon.
Thank you very much. Appreciate you guys coming. Sure, it's nice to be in person again, though, I'll tell you.